So, good afternoon, everyone. So, today we have Professor Babutosh Chanda to deliver a webinar on morphological network. So, a bit about the speaker. So, Professor Chanda received his BE in Electronics and Telecommunication Engineering and PhD from University of Calcutta in 1979 and 1988. His research interests include image and video processing, computer vision, and mathematical morphology. He has published more than 200 technical articles in referred journal and conferences, authored two books, and edited 6 books. He has received Young Scientist Medal of Indian Science Division Academy in 1989, Computer Engineering Division Medal of the Institute of Engineering, India in 1988, Vikram Sara, I'm so sorry, Vikram Sarabhai oh, Research Award in 2002 and IEIT Ramlal Vadva Gold Medal in 2007. He is also a recipient of UN Fellowship, UNESCO INRA Fellowship, and Diamond Jubilee Fellowship of National Academy of Science India. He is a fellow of Institute of Electronics and Telecommunication Engineering, National Academy of Science India, Indian National Academy of Engineering, and International Association for Pattern Recognition. Currently, he is a professor at Indian Statistical Institute. So, with that said, the stage is over to you, Professor, and I will be present there for any issues.
Okay. Thank you, Turun, for nice introduction. Let me share my presentation. I have a bad throat today, but anyway, I hope that won't bother much. Yeah,
Any issues in screen sharing, sir?
Can you see the PPT? No.
Okay, so can you please share your screen again?
Yeah. Um,
Okay.
wait, it's not share screen and again share screen. So I'm here.
Your entire screen will be.
It's not coming.
Um,
So I'm sharing myself. Right.
okay, yeah. Open the PDF, sir.
I've
Okay,
already
okay.
opened the PDF. Okay. Uh,
Okay.
so it's there.
Okay, sir, click on the share button once and share screen.
Share share button once, share screen. Then again, it's down the side, share screen is a blue, right?
Just a moment. Yeah, again click share screen.
Yeah. You are on the show. It's
Okay, just open the PDF now, sir.
no,
Yeah,
cannot see. Can you
yeah.
see?
Yes, sir.
Yes. Okay. So thanks. Can you see the PDF? Fine.
Yes, sir. It's visible.
Okay. So sorry for the initial
No, no,
trouble.
sir. That
Uh,
happens.
okay, that's fine. Okay. Hope we'll talk about morphological network today. Okay. Um, this presentation actually integrate two different ideas which ran parallelly for a couple of decades. Uh, one is a mathematical morphology, another is a usual neural network. Now, mathematical morphology usually deals with image information, which directly operates on the shape of the objects present in the image, and that's a nonlinear operator. Okay. On the other hand, convolution neural network is another technique which is being used very widely for a couple of decades. Last after LeCun has presented his work and gave an amazing result on MNIST data. So we'll just try to present here that how these two different ideas can be integrated for applying in the computer vision problems. Okay. Um, the result I'll show is mainly the PhD work of two of my students, mainly of the Ranjan and also Sanchan, who has already done his PhD, has helped him in developing the idea and applying it to the various computer vision problems. Okay. So, what is morphology? This is nothing but a non-linear image processing tool which is useful for processing and analysis of geometrical structures in the image. It's particularly geometric structure because the operators basically defined in terms of set theory, lattice theory, topology, and random functions. Now, the set theory is basically takes of the set of pixels either in a flat intensity or have any topological surface type intensity variation. Lattice theory ensures the order of the operands and the operators, and there are many applications on that. Very basic image processing or image uh, analysis type of application like boundary detection, skeletonization, filtering, convection, thinning, and these together applies to any real life problem. And many of the real life problems where we have to deal with the shape information, uh, like granulometry, uh, filtering out the grains in different sizes. Morphology is the most efficient tool. Okay. Uh, to start with, I just started to present two most elementary operations defined in the field of morphology. That is, one is about the dilation and another is the erosion. In fact, these two operations are dual operations. That is, if you define your image as a two regions as the objects or foreground and background, whatever we do by applying the dilation to the foreground, exactly same thing, same result you can obtain if you apply erosion operation on the background and the vice versa. So dilation is nothing but uh, defined as the value of output pixel is the maximum value of all pixels in the neighborhood, And this neighborhood is defined by what we call the structuring element. Similarly, for the erosion, the output is the minimum value. So dilation erosion is what I said already. This is a dual operation. One is a maximum, one is a minimum, and both the operations are applied using what we call the probe or kernel, particularly in terms of morphological area. We call this structuring element. So structure element actually defines the shape of the neighborhood around the pixel which is going to be processed and whose output we are interested in or we want to analyze the particular area. Now, this can be simply mathematically defined as the given a structure element say S D, which may be defined taken as the structure element for the dilation. So given that image I of xy, we can apply pixel wise the value of SD so that their value changes, and then we take over the maximum of those values over the domain defined by the SD, and that gives out the dilated image. Similarly, for the erosion, only thing is expect instead of the addition, we use the subtraction here, and instead of max, we use the mean. Okay? So this SD and SC is nothing very particular. You can define any structure element S, and you can define your dilation or erosion operations. So it will be much clearer if we use some example. Suppose A, the picture on the left hand side, this rectangle is the input image. We call it A, the object here. And I have a structure element, the circular one, denoted by B. If I dilate A with the structure element B, the output I get A dilated B, which is nothing but whatever they are present in the A is there. But in addition to that, there is some portion of the background is also appended to the object. So that increases the area of the given image A, right? Or given object A. No, it's not the, you see this, it's not the magnification. For example, there is in A, there are two different components, one at the top and the bottom, and there is a gap in between. If I had taken the magnification, the zooming, what would happen is even this gap would have increased. But here you see this gap is filled up. Here you see the gap is filled up, and this thing is really giving you the dilated image. If I use the erosion operation, then it takes the basically some portion of the image where it actually bring it what is called the bring it actually the only that portion of the image or center of the image where the structure element can be contained. So for example, here the bottom part of this component is not wide enough or the large enough to contain the structure element, so it is gone, it's vanished. Okay, it is removed. So these two are basic operations of all the dilation morphology, and we can define many different algorithms based on these basic two operations and their combination, of course. For example, here we have some image cells in the image, and it has a very jagged boundary. So if I first we take an structure element, say GIS type structure element, we first erode so that all the small components can be erased out, vanished, and then we again dilate them. We can probably get back the very smooth boundary and serious objects of significant sizes. This is the binary image. If we go for the gray level image, there is a lots of uh, salt and pepper noise in the on the left hand side image. We take the erosion followed by the dilation with only a 3 by 3 small structure element. We see that most of the noise is gone. Okay? And there is another application where we have an image which has lots of grains. These are actually mineral surface uh, micrograph taken to the microscope. Uh, Now that contains lots of grain, but of different sizes. I want to filter them out for different sizes. What I do, I convert it to binary image by thresholding, followed by uh, some erosion dilation operation depending the size of the structure length. Some grains survive, similar grains. Not all grains are not survive. So, which grains will survive can be determined by the size of the structure element. So, what are the challenges? If I design a algorithm, computation algorithm based on the size of the based on the using the morphological operators. First, we have to define the size of the structure element. That means what type of objects or what size of object grains we try to filter out. Number one. Second is what is the shape of the structure element? The circular, the elongated one, rectangular, ellipsoid. There are many regulars or maybe irregular ones. So it will define the shape of the structure element. Then there are operations like so far what we have learned is the dilation and erosion. Which operation is useful? Whether dilation or erosion, or maybe both, with some order. Then we have to determine the what should be the sequence of operations. So these are the problems we have to really face when we design or develop a morphological algorithm to solve a computer vision problem. Okay? There, I repeat again, there are three problems: size of the structure element, shape of the structure element, and which order will apply the what kind of operation, dilation and erosions. Yeah. So it's even harder when it comes to grayscale of the color image. In the binary image is a little bit simpler, but in case of grayscale of the color images, the problem is much more exaggerated. Okay? So our first objective is to check whether this structure element can be learned by some means. Now we know already that neural network and more appropriately convolutional neural network can be used to process the images where we apply the convolution operator based on some rectangular kernels, and the elements of the kernel actually produces different kinds of output, and this it actually extracts different kinds of features from the image. Now, conventionally, we used to design these kernels for convolution operator. Now the CNN, or the convolutional neural network, or the deep learning network, actually gives us the capability, that gives us the power that we can learn or the train the structure appropriate for a particular applications. Okay. So using that, suppose I want to apply my morphological operators on some rainy images on the left hand side. You can see a tiger and with the rainy environment. Whether these raindrops can be removed and I can see the tigers in the clear environment. Okay. Uh, so we need to what we call the some dilution operator using structural element. Okay. Uh, but we have to determine the size and shape of the structural elements and also the order of the dilation of the erosion operations we have to determine so that we can get the deranged image shown on the right hand side. Now, this kind of determining this is kind of problem where we need to determine the structure, shape, and size of the structural elements. We can apply our network so that we can learn the structural elements. We can learn the structure elements, right? Now, in reality, the different rainy images have different shapes and sizes of the raindrops. So, what's the problem? We cannot really develop our algorithm for a particular set of images. It should be as general as possible. And there is the problem of the structure element that can be used for the one kind of images may not be suitable for the others. So we need to develop or we need to design a structure element. We need to train a structure element which can be applicable to a large set of images, different problems. Okay. So that's the question. What should the shape and size of the structure element in general? And what should be the order of morphological operators to be applied? Which order will apply the dilation and erosions? Okay. So what we did basically applying the dilation erosion operator in different order and try to learn which path or which particular combination gives us the best result. So before doing that, we just relook at the definition of the dilation and erosion operator. If you remember the convolution operator between an image and the kernel, then there would have seen as the image I multiplied by the kernel and taken the sum in discrete domain. In analog domain, it is the integration. So here, convolution operator and dilation operator are both the we know there's a neighborhood operator, and the neighborhood is defined by some window in case of convolution. In case of morphology, it's defined in terms of the structure. And instead of multiplication, we take the addition. Instead of summation for the convolution operation, we take the max or min operations. Okay. So, but it's the same architecture, same structure of the convolution neural network or deep neural network can be used for train the morphological structuring element or the morphological probes or the morphological kernels by using the same set of algorithms or same set of architecture or the network what we have already tested for the convolution neural network. So basically the dilation and erosion operations are practically nothing but the morphological neurons. And we have another advantage here is that in convolution neural network, after each convolution layer, we have to apply a kind of activation function which is non-linear, either sigmoid function or ReLU or can hyperbolic, whatever is the all unknowns. But since max and min are already non-linear operator, we don't need to use any further nonlinear activation functions. Okay. So pictorially, what we see is there is an image. We have a structural image or the kernel like this one. So you add the values with this one, the value of the kernels, and then take the max to get the output value. So there's a, and now the whole image is being traversed by this kernel, pixel by pixel. So it's a roam around this one as a raster, just like a raster stack. So how do I learn the morphological network? We build a network using the dilation operation in any arbitrary order. It doesn't matter. We'll show that there's if some layer, some dilation or erosion layer is not relevant, or is if it is redundant, then it basically takes a spike type or also identity type structure element so that there is no change. And then we randomly initialize all the structure elements of the network and define the loss function just like any convolution neural network, and then we go on learning or train the network by means of back propagation algorithm. Now, back propagation algorithm requires some taking the derivative of the output in terms of the parameters using the network. Unfortunately, both the dilation and erosion operations involves max and min operations, and that is basically non-differentiable. Okay, but fortunately, though that's not differentiable everywhere, but they are piecewise differentiable. So, except those places where it's not differentiable, we can use the term subgradient. Otherwise, we can use the usual differentiation to for our feedback operations. Okay. So this is the network we use. So there is an input image, and there are two different paths we just see, and one path starts with some dilation operation followed by erosion operation. Another path starts with the erosion operation followed by dilation operation, and it goes on. Okay, until we reaches the single layer by combining them, and then we apply some kind of combination layer to the combination, and with these two different weights. One weight which called the WO, that's the open path weight, and another weight is WC, closed path weight, and they are basically linear combination to give us out. Okay. So the noise can be, we know this can be positive or negative, dark or bright. Noise are random numbers, usually zero mean with a symmetrically distributed. So the negative or the dark noise are actually removed by the path 1, and whereas the positive noise or the bright noise will be removed by the second one, and then we'll combine to get the output. So these multiple dilation erosion layers can deal with the various spatial patterns in the image, and that gives us the out. So these are the, on the left we have the input images which are rainy scenes. Output of the path 1 is something like this one. Output of the path 2 is this one. Okay. When we combine these two and generalize as a morphological network, the output is much clearer, more general, and so this is the qualitative result. And if I go for the quantitative result, what is so there are images and a large number of images. We take as a show the only average performance, average over a few hundred images. So where the From the input image, where the rainy image along with the ground truth data, we measure the rainy image as only 24.3 PSNR, SSIM value 0.85. We applied the path 1 for morphological network, and as well as we have compared with the traditional convolution neural. Now we see this convolution neural network improves the PSNR value from 24 to 29.12, whereas our morphological network improves only up to 20 PSNR. Okay? Surely it's a little less than this. However, SSM measurement, quantitative measure, it shows 0.92 here and 0.92. One is the best idea, but 0.92 is quite good. These are the results for the path 1 and path 2, but I'm not right now looking at that. Now, well, but you see this performance-wise, SSM is same, but in case of PSM, we are little less. We have another advantage. We didn't really look at it. Number of parameters. If I take the number of parameters for CNN is 100, in that case, number of parameters, our network is only 0.27%. Right? So if there are 10,000 parameters or 2,000 values you need to train, we see this only 27 parameters you need to train in case of morphological network. Okay? So there is a huge advantage over training and the computation cost during testing. So you see, it's a major advantage of that one. And if we even reduce the size of the structure element network, we can even go even further in the number of parameters, though performance is not that good. Okay. This gives us two ideas. Okay. Number one, we learned that structure element can be learned from in the form of the network. Right? And secondly, it needed very less number of parameters compared to traditional convolution neural network, and that not that much significant, but we know there's a path two. Second path gives better result than the path one. Okay, but the first two observations are more important to make a more complex or more complicated applications. Okay? So what we learned, that's what we get the idea that structure elements can be learned. So we need not design the structure element, its shape and size, etc. through trial and error. It can be learned through the network. Okay? And we need very less number of parameters, so everything is very fast. In morphology, there are two more useful operators, which are open and the close. Opening is nothing but, we'll say, the combination of dilation and erosion. Closing is also dilation, combination of dilation and erosion. And these two operations are again dual operators. So what we do on the foreground by the opening, same result can be obtained if we do closing on the background. Or it's complete. Okay. So in opening, we retain opening operation retains only that part of the object that can contain the structure element completely. On the other hand, in closing operation, some portion of the background is appended to the object. Which portion is appended? The part of the background which cannot contain the structure element. Just the opposite, you see, in case of object, in case of open, the part of the object which cannot contain the structure element, that is removed. Only which can contain structure element, that can retain. On the other hand, in case of background, the part it cannot contain is appended to the object. Thus, this open and close are basically the filters. Okay? What is a filter? Filter has some property. Okay? Filter should be increasing, Ntx, okay, idempotent Ntx. So we can define the opening of image I with the structural element S subscript O by first eroding I with the suction media. So then the result is dilated to get the open result. Similarly for the closing, we first dilate the image by a structural element say S subscript C, and then the result is eroded to get the closing operation. So both open and closing are defined in terms of structural element, uh, same structural element, and they are just a combination, concatenation of the two operation, opening and sorry, dilation and erosion. Open is open operation is nothing but erosion followed by the dilation, and the closing is dilation followed by erosion. Now both the operations are increasing and idempotent, so they are the filters. And in particularly, in particularly, the open we call the anti-extensive. That means opening result is a subset of the original set. Okay? That means after pruning some portion of the A, we get the open result. Okay? So some portion is pruned out, removed from the A. On the other hand, closing operation is extensive. That is, it's a superset of the original one. That means some portion of background is appended with the object A to generate the closing result. Naturally, that will be the superset. In case of functions, right? Because this is the binary set. When I talk about the functions or the image, in opens image after opening is usually, if we compare pixel wise, it will be either less or equal. But in case of closing, the function value will be either greater than or equal to at each and every pixel. So opening operation is a some kind of a lower bound or lower boundary of the image, given image, and closing was a some kind of top cover or the upper boundary of the given image. Okay, so suppose I want to implement the dilation operation. I insert or the given as input the image X. I want an output Y which will be dilated version of the X. But since I don't know the what will be the order of the structure operations, erosion and dilations, since I suppose I don't know, I put both the erosion and dilation layer one after another and input X to the network. The output will be Y, which is the dilated Y is the dilated version of X, and we see the structure element. The trend structure element shows that erosion there is only a kind of a spike called the identity operation, whereas in the dilation we have a kind of this step structure. So since this is the second structure element for the dilation, so dilation occurs, but since but not erosion since the structure element is very different. Exactly other way, if we want to do the erosion structure element is painted like a disc or the rectangle, and the dilation structure element is almost like a spike. Right? So even with this dilation erosion layers in the network, the structural element will be trained in such a way some layers will may be made irrelevant. compared to, or the irrelevant compared to what we want to get at the output. In case of say opening, both erosion and dilation should be involved, so we get an output. If I increase the number of layers, we see the same structure elements as broken into different structure elements, which again by combination will generate the same structure. Similarly, for the closing, we see this. It starts with the erosion followed by dilation followed by erosion, but closing requires only dilation followed by erosion. Closing requires only dilation followed by erosion. So this erosion layer and this dilation layer is irrelevant, redundant, and you can see from the chain structure element that this structure, this point structure element and this very small structure element actually make these two layers as irrelevant. Only significant structure element is for the second dilation and the second dilation. First dilation and the second dilation. Okay, so even if we have multiple layers of dilation erosion, depending on their requirements, structure elements are changed accordingly. So, for example, we have some input and we want to have this output. There is a erosion dilation operation such that we want the open result here. So both the erosion and dilation structure are they have the significant shape and size. Now this particular result is shown for training the image network for using the 400 images from the Flickr data. Now one interesting thing is if you go for the traditional definition of the uh, opening or the closing, we see for the opening, both erosion and the dilation are made using the same structural element. Whether it's for opening, whether it is for closing, the same structure element. Okay. Now, what you see here, even in the previous example, right? Opening and closing. But you see here, these two structure elements are not same. Then how do they guarantee that opening operation happens? Now, though these two structure elements are same, uh, it can be mathematically shown. In fact, it is proved in one of our publications that in a special circumstances, even the structure different structure elements can generate opening result, which is usually for convenience defined using in terms of the same structure. Same result, I repeat, I reiterate that same opening out result can be obtained using the different structure element for the erosion and the dilation. Okay. And that's why the change structure element is doing the very successful job. Now, before employing them this opening or the closing operations, we need to really verify if these operations, opening operations using different structure elements is a really valid or not. So let's look at the Ntx Sensor operation, which shows us in case of opening, the opening of function f is less than equal to the original function. And the idempotence of openings are says that if I open some function, the result we get is same as the if I go on opening the same result again and again. And increasing operator shows that if function f is pix at every pixel is less than the function g, then after opening, the still f remains less than or equal to the function. This is the increasing operation. Now let's prove that's a increasing property. the given n function f, we generate a new image which is a greater than this f, right? So how do you get this f? F hat? We multiply this f with some value k and then add some random number to it between 0 and 1. So if k is greater than 1, what will happen? It will be magnified or the value will be larger, and after that u0 is a random number from the uniform distribution from 0. So this shows that the function f hat is greater than or equal to f for at any x. Okay? So based on that, we use the check the increasing operator. Since we know the f hat or f is less than equal to f hat, then we must get the opening of f is less than equal to opening of f. This is this. So if I take opening of f minus this one, the value will be negative. Okay. So what we find out? Some error function where we subtract from this lower value to some preferably higher value. So this value should be negative, maybe negative. Okay, if my increasing property fails, this value should be. So if this value is greater than 0, okay, it's supposed to be negative, or at most is a 0. But if it's a positive, my increasing property fails. So find out for all positive values, we add up and try to display it. But this E shows that the value are all 0. Okay, at all every pixel the value is 0 because the value is here. None of the values are really positive, so everything will go to 0. Okay, so increasing property is very good. In case of Ntx Sensor, exactly same thing. This value is less than this one, so we take the difference between the lower value minus the higher value. If the value is positive, then my antecedent property is there. Right? So if it is greater than 0 or positive, we add up the value and try to display it. Again, we say there is no positive value. Every value is 0. And finally, for the idempotent property, we just open any function, then same function, open function is opened again, and we take the difference between these two. This, if they are same, the difference will be exactly 0, neither positive nor negative. Okay? So this value is neither positive nor only 0. So you say they are a little bit. Okay, we agree that a little bit, very small perturbations here. It's not always 0. So it very closely, not perfectly satisfy the idempotent property, but very close to, very close to. So what you do, we now are more or less satisfied that my opening operation, even with different structural elements, are doing the right job. Okay. So we can generate our closing network by applying a dilation of layer followed by erosion layer followed by dilation layer followed by erosion layer and go on doing it. There are multiple layers so that X is the input and Y is the output. For the opening neck, we may start with the erosion layer followed by dilation layer and goes on appending many such layers and finally out. And in case of open closed network, what we do, we use both the path, one for the opening path and another for the closing path. Then we estimate some weights to combine them, and then the combined value is made a segment operations to get the Y out. So here is the opening closing network, and let us see, we just try to process this image. Here's a combine or append everything together and convert it to linearly combine to get the only three layers, three color layers. Then the color layers segment function is applied to bring it to the range from 0 to 1. There is a minimum to maximum value, and there is the output. Okay. So this opening closing network, depending on the application, depending on the output that we want, given the input, the structural elements are trained to do different kind of jobs. So for deraining, you can see the color images. This is the input frame. Lots of rain droplets are there. This is the closing net. This is the opening net, and this is the basically the opening and closing net. Right? This is a traditional convolution neural network using lots of parameters, millions of parameters, and this is the ground. So you see, we are very close to this. Both the results are very close, the opening closing network and the CNN network, but with much less computation cost. And this is the graph. This is another set of rainy images, and we look at only at the final result. For the CNN, you can, if you look carefully, still you can see some rainy state, but we are almost free of that. So if we look at the quantitatively, we see this the results are very close to CNN and the morphological network for the color image, and this shows the SSIM and the PSN values are close to each other. We apply this network to another application where we are applying the dehazing. Dehazing is nothing but remove the haze or fog or mist from the image when we take in the morning of the winter days. There's a lots of haze or the fog in the environment. So JX is our ideal image. Because of fog, the reflected light is basically scattered. So it's a transmittance value T is less than 1, and we get less amount of reflectance or the image information less than this G, and we also have some additive, uniform additive air light that looks like a veil type. Okay? So if I just simplify this one, put as a constant term, but at each and every location it's different. Okay? So what we do, we apply a similar kind of opening path and closing path, combine them, and then we again put another set of it. Now they are again individually. Now one particular output gives the transmitter matrix, another is the air light image. So using these two, we can simply dehaze this image. Okay? So all these structure elements of kernels are basically trained through this network. And this is the quantitative result first, then I'll go to the qualitative result. So there are many different algorithms available in the literature using mostly the neural network and some traditional ones using the conventional technique or physical model. The most closest one, the Zhang et al. Paper, right? And ours is the all this information can be found in our paper. I'll show give the reference at the last. And this is our result. You see 0.73 SIM, and we have 0.75. 0.66 SIM, 0.75. It goes on, right? And in terms of SSIM, our result is always better, which is more modern measurement. In terms of PSNR, ours are a little worse than the closest competitor. But anyway, in all the cases, is much better than all other algorithms. So this now we see this is the hazy image. On the left, these are the input images, and this is the ground truth. This images were supplied in the CVPR conference. They have organized and competition of and the data set they supplied they call the OH data set for the competition. Well, so our results is like this. Now from the image we estimated the transmittance matrix, which is this one, L light matrix, L72 bluish, like this one, and this is our result, our output, and this is the ground. It's a very close to ground truth. In terms of ours is a little greenish, where there's little bluish. Then another set of images, which is another benchmark data set. 3 images. This is only qualitative result. This is the second column is the transmittance matrix. Third column is the L light. There is the pale type result here, and the final one is our output. Okay. So you see this the same network, almost similar network, using the or training the structure elements can produce different kind of outputs depending on the shape and size of the structure element obtained from the same network. Okay. These are some of the publications from our lab, co-authored by the Ranjan, whose results are basically shown here. For detail of these things, you can look at this journal paper, Method Morphology Theory and Application. Here we have really presented the whole network and this news concept, putting the morphology and the convolution neural network together and applying the various computer vision problems. Okay. Thank you, and thanks a lot for your attention. I'll be happy to receive any question.
So, thank you so much, sir. It was a good session. We don't have much questions, just 2 questions as of now.
Okay.
One thing, this question was asked at approximately 3:15 p.m. It is,
Okay.
where do we find the use of an eroded image?
Can you repeat the question?
The question is, where do we find the use of eroded image?
Okay. I believe the person who has asked the question has some idea of the image processing. So one of the major application of the image processing is the extracting structural information of the object from the image. Okay, and traditionally we do use it. We do use the thinning or scaling medial axis transform. Okay, any standard image processing books contain them. Okay, either thinning or the medial axis transform to generate the skeleton of the objects, and that skeleton actually gives the structural information, structural description of the object. Okay, and in that case, actually what you do, like something like your onion filling, we just go on remove the outer layers of the so until I go to the core of the object. Okay, the same thing can be done by using the erosion, because we are removing some part of the object, where I can fit my structure. Okay? So this erosion operation, if applied repetitively, we can generate the skeleton much more general way. Okay? So we may need a proper network with trained structure element, and through the iteration we can generate the schedules. Did one kind of application where erosion, erosion operation, or the erosion network can be used.
Okay. And so,
Okay.
second question we have is, with considerable if and else issue, isn't this algorithm as complex as CNN?
Ah, yes, it's as complex as CNN. If I go for the order of computation, the same order of complexity is there, but there are two advantages. Number one, we take the addition in place of multiplication. This is the one advantage computationally, and you may consider the max can is taken as the, but it's not the only one. It's the only minor one. The major one is, whereas I have shown that, whereas I need 10,000 parameters to be trained for implementing the CNN algorithm or CNN convolutional neural network. This morphological network can do almost a similar task, but using only the 27. So there is only 0.27% order of uh, parameters are required. So you see a huge savings in terms of training the parameters, number of parameters, training, and also at the time of testing. Okay? Where I mean, clear, there is the advantage. In if you consider the order of complexity, no, they are the same. But if you really count the seconds, this is a much faster.
Okay, sir. With that, we are done with the question. And I think it's the time to call off the session. And I think we did overshoot our time limit. And I think that's why most of the people have left that, because we had
Oh,
crossed the limit of 1 hour. Okay,
okay,
so thank you so much, sir. It was a pleasure hosting you, and I do hope that Team Especially would like to thank you for giving your time, and we would love to host you again. Thank you so much for coming to the webinar.
okay. Thank you, Tunun. Actually, I counted from where I started the lecture, because first 2 minutes was print. Anyway, thank you again for inviting me. I'm really happy to give the webinar. Thank you.
Okay, thank you.